Hello everyone. So previously we had discussed on the topic sieve of Eratosthenes, right? So this is segmented sieve is nothing but this is the optimized version of the sieve of Eratosthenes. Let's see the same here. Let's get into the definition part, man. So what does the definition part say here? The segmented sieve algorithm is an optimized version of the sieve of Eratosthenes used to find all the prime numbers in a given range L, R, right? Especially when R is very large, right? So it divides the range into smaller segments and it uses pre-computed small primes to mark non-primes efficiently. Let's move on with the explanation part here. So the sieve of Eratosthenes, what it does, it efficiently finds all the primes up to the square root of r. So this one we have discussed already. We know the sieve of Eratosthenes. The previous algorithm was this one, sieve of Eratosthenes itself. Yeah, the sieve of Eratosthenes, what it does here, so it efficiently finds all the prime numbers up to square root of r. This we know. So what does the segmented sieve do here? The segmented sieve then uses these small primes to mark multiples in each segment, L, R. So this part is very important. Yeah. What it does, it uses these small primes to mark the multiples in each segment L, R. So basically this approach avoids storing an unnecessary large array where R is big, right? So we can just consider up to 10 to the power of 12 here, suppose for the example sake. So let's see the algorithm steps here. So listen to this carefully. The same thing will be articulating in the form of code. So the first thing here would be, we have to find, suppose if you have to find all the primes up to the square root of or using the normal sieve, right? So we will be creating a Boolean array for the segment L, R. First, we will find all the primes up to the square root of R using the normal sieve of Eratosthenes. Then what we'll do, we'll create a Boolean array for the segment L, R. Second step, we'll be going with a Boolean array. Just remember this one. The same thing will be articulating in the form of code as I've said. So for each small prime P, what we'll do, we'll mark its multiples in L, R as non-prime. For each small prime P, what we'll do, we'll mark its multiples in L, R as non-prime. So remaining unmarked numbers in L, R are just prime numbers or prime. Yeah. So this is it for the this one. What do we call? Explanation part. So now let's try to implement the same thing in the form of code. Yep. So let's start writing the algo here, segmented sieve algorithm. First step here, so we have to go with a simple sieve to find the prime numbers up to square root of r, right? So first, let me import math here. So let me give here import math as this one. As discussed, let's go with a simple sieve just to find the prime numbers up to square root of r. So I'll just go with the def here. Let me go with simple is this one, simple sieve actually. Simple sieve of let me pass the limit. So this is fine. Yep. Now the next part is, let me go with the sieve here. Let me go with the sieve. Let me set this one to the boolean value true into let me give limit plus one. Yep. So this is fine, I believe. The next one is sieve of zero equals sieve this one. Sieve of zero equals sieve of one. Let me assign this one to the false. Yeah, this is also fine, man. The next step, let's move on with a for loop here. For num in range, what's the range actually we have to go with? From 2 to this one. I'll just go with the int of, so we have already imported math, right? So I'll just make use of here, not match actually. Math dot, let me go with the square root here. Math dot square root of, let me pass the limit here. Limit, this is fine. Limit plus 1, usually n plus 1, right? So this one we can just write it in this way, int of math dot square root of limit plus 1. Yeah, if you are making use of the math operation. So this is fine. Now let's go with a simple if condition. If sieve of, let me pass the num here. So this is fine. What if sieve of num? Then we have to mark the multiples of the number as non-prime. So let's go with a for loop. So this one for multiple, for multiple in range actually, for multiple in range. So this one will be number into number, nothing but num into num. Also we have to go with the limit plus one. Again we have to go with the number. Yes, so this is fine. So within the for loop, the first thing is let's set the sieve of multiple here. So multiple or multiples we consider multiple itself, right? Sieve of multiple. Let's set this one to the Boolean value false. Now we have to return all the numbers that are marked as true, basically the primes, right? So I'll just come here. So let me return mm, I for I in range, I for I in the range. So this one has to be 2 comma limit plus 1. Yeah, I'll just go with the limit plus 1. So this is fine. I'll just go with here. Did I do anything wrong here? 1 second. Closing this one. This is fine. Yeah. Let me give here if sieve of, basically let me pass the I. Yep. Yeah. This is the first step. We have went with a sieve of normal sieve, right? So this is fine. Next, what we'll do, let's go with a segmented sieve just to find the primes in L comma R, right? So I'll just go with a function here, segmented this one, sieve actually. So let me consider the parameters L and R as discussed, right? So next one, let me consider the variable limit here. So let me assign this one to the int of, again, math dot square root. So this is showing here. This is fine, man. Yeah, math dot square root of R, basically square root of R plus 1. Yeah, plus 1. Then let me consider the variable primes and let me assign this one to the simple sieve, the previous function that we have written, simple sieve, and let me pass the limit here, limit. So now, as per the discussion, what we have to do, first thing is we have to find all the primes up to the square root of R using the this one normal sieve. We have done this one from the line number 23 to 33. So this is fine. Now, the next step, if you remember, or we can just clearly see here, we have to create a Boolean array for the segment L comma R. Let's do the same thing now. So let's create the Boolean array for the segment L comma R. So I'll just go with the is prime variable name here. Let me set this one to the Boolean value true into, so I'll just go with R minus L plus 1, R minus L plus 1. So the next step would be we have to mark the multiples of small prices, small primes actually in the range, right? So let's move on with the iteration part in simple terms. So this one will be for P in the prime. So this is fine. So we have to find the first multiple of P in L comma R. So let me make use of the start, this one variable name. So this one will be max of P into P L plus this one P minus 1. This is also fair by this one. What do we call? P into P. P into P. Next, let's move on with a for loop here for J in range. For J in the range. So let me call start here. Start. And this is fine. R plus 1 is also fine. Then let me pass the P here. So this is also fine. So the next step would be, let me go with is prime. Is prime actually of J minus L. Let me set this one to the Boolean value false. Boolean value false. Yep. So now we are done with this part. What shall we do next actually? We have to handle the case when L is equivalent to the 1, because 1 is not prime, right? So we have to handle that particular case as well. So I can just write it in this way. Let's write the simple if condition for this one. If L equals 1, then what we need to do? Let me call the is prime here. Is prime of 0, we set this one to the false because 1 is not prime, right? So I'll just go with the false here. Let me set this one to the false initially. Now we are left with the last step, nothing but here we have to collect and print the prime numbers in the range actually. So I'll just go with the primes in range. So this one will be L plus I for I in this one, basically range for I in range. So this one will be R minus L plus 1. R minus L plus 1 if is prime of if is prime of I. So then let me return, what shall I return here? Primes in range, right? So this one, primes in range. Yep. So now let's do one thing. Let's move on with the last step or the this one example usage basically. Yeah, we are done with the algorithm. This is it for the algorithm. Let's move on with the this one. What do we call example usage? So I'll just go with L. Initially, I'll consider 10. We have to consider L and R, right? So R, let me consider up to 50 from 10 to 50. Yeah. So this is fine. So let me go with the result variable here. Let me assign this one to the segmented sieve actually. Yep, segmented sieve of, let me pass L as well as the R, the value 10 and 50, from 10 to 50 actually. So let's print something for the interactive purpose. So I'll just start with the F, as we'll be going with the string interpolation. So this one will be prime numbers between, so this one has to be L, and let me pass the R as well. Let me pass the R as well. So this is fine, I believe. So finally, let me print here this one result actually. Yeah, let's print the result. So this is it for the algorithm, the simple one. Yeah, so this is it for the algorithm. Yep. So now let's do one thing. Yeah, as we are completely familiar with the algorithm, so we have discussed this one step by step, right? So the same thing, whatever we discussed in the explanation, we have articulated in the form of code, right? So now, if I run the code, what is the algorithm actually? Sorry, what is the output that we need to get here? Basically, see, we are printing the prime numbers between 10 and 50, right? 10 and 50 basically. Yeah. Prime numbers between L and R, nothing but we have considered prime numbers between 10 and 50. So what's the output that we need to get here? 11, 13, followed by 17, 19 as well, and 23. So we'll go with the 29. We'll be going with the 31, 37, 31. So we'll be going with the 37 as well. Then followed by 41, 43 as well as the 47, 41, 43 as well as the 47. These are the prime numbers between 10 and this one, 10 and 50 actually. So you can just count here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 prime numbers actually. Yeah, 11 prime numbers. So this is the output that we need to get actually basically when we write the code, right? So here 10 is not prime, right? So 10 is not prime. So how does the algorithm work? I'll just explain you. See here, we are considering from 10 to 50, right? So 10 is not prime here. 10 is not prime here, right? So this is not prime. So what we'll do, we'll go with the next prime actually, which is 11. 11 is prime, right? So next we will be considering after 11, we will consider actually 12, 14, 15, this one 16, 18 as well as the 20. So these all these numbers have the divisor. So we will skip this one. We'll not be considering this one. We will be skipping this one. Yep. So we have 13, 17, 19, 23, this one, 29, and so on, right? So these are the primes basically found between the L comma R. So first we'll skip this one, and these are the primes that we will be finding within the L comma R, nothing but between 10 and 50. Yeah. So this ends at 47. This ends at 47. See here, this one. This ends at 47, which is the last prime. Nothing but it is less than or equal to 50, right? Between 10 to 50 we are going between 10 to 50 we are going with. So these are the prime numbers we'll get accordingly with the algorithm. Starting with the 11 actually, 11, 13, 17, 19, 20, 29, and so on, 31, 37, 41, 43, 47. Yeah. So these 11 numbers we need to get. So let's check the same. Now we have the complete idea, right? So I'll just copy the file name. Let me give Control J here. Let me type Python followed by the file name. So prime numbers between 10 and 50. See here, 11, 13, 17, 19, 23, 29, followed by 31, 37, 41, 43, and 47. We are getting the correct output here, right? So we are getting the desired output. Yep. So this is it for the algo. We have the complete idea of the algorithm, right? Along with the example usage we have went with. So we have complete idea on the algorithm segmented, right? So, yep. Now let's do one thing. as we are done with this one segmented sieve algo, let me summarize whatever we have learned so far, right? So we have to remember these 3 to 4 points. So this is very important, right? So um, first thing here would be this one, sieve of Eratosthenes here actually. Sieve of Eratosthenes. What does it determine basically? It finds small primes efficiently, right? What it does, it finds the small primes efficiently, right? So we will be getting the many opportunities to implement this one, sieve of Eratosthenes or the segmented sieve. Most of the times we go with the sieve of Eratosthenes, that's enough. But usually segmented sieve, if you are doing CP, you'll get many opportunities to implement, not to worry, right? So now let's move on with the next step here. Segmented sieve, what it does actually, it extends the logic. Basically, this one segmented sieve is the extension to the this one sieve of Eratosthenes, right? So segmented sieve, it extends the logic to very large ranges. So this acts as an extension. Segmented sieve acts as an extension to the sieve of Eratosthenes, the normal one. Segmented sieve extends that particular logic to very large ranges by processing smaller chunks, right? The space complexity is reduced to the space complexity is reduced to because of r minus l, because of r minus l plus 1. This is fine, instead of because of r, instead of because of r, right? Instead of because of r, this one, what do we call, the space complexity will be reduced to this one because r minus l plus 1. Yep. So now the final step is efficiency. Let's discuss about the efficiency. It is efficient for the very large inputs, like suppose it may be 10 to the power of 9 or 10 to the power of 9 plus 10 to the power of 6, right? So it is very efficient for the large inputs. Just for the example sake, I've considered this one, 10 to the power of 9, 10 to the power of 9 plus 10 to the power of 6. Yeah. So this is the efficiency basically. So these are some of the points that I found was very important actually, right? So this one you have to remember along with the algorithm. Try to remember these things. Yep. So you don't have to mug up. Just this one. Try to remember certain things that is related to the algorithm. Yeah. So yeah. So this is it for the this one, segmented sieve algorithm, right? Very simple one. So we are done with the algorithm. So we are done with this particular algorithm. So next, what we'll do, let's discuss this one. What do we call Euclidean algorithm to find the GCD or the greatest common divisor, right? So here also we have normal this one algo, first algo Euclidean algorithm, and then we have the extended Euclidean algorithm, right? So this is the extension for the this one Euclidean algorithm. These two algorithms, let's discuss this one tomorrow. For now, so we are done with the segmented sieve algorithm. For now, this is it. Thanks for watching, guys.